Mike.
Okay, thanks. What I have on the screen right now is kind of a plan for what I want to get through today. So it's a little bit ambitious, so I hope it's not too fast. Go ahead and stop me if you can. Always difficult, but yeah, I want to start with kind of a recap of what we did last time. Is that this character basis is the pre-image of a Schur function in the Frobenius map I had. And I'm going to do one more example just to make sure it's clear how it works. And then I will say, hey, this is how you compute it. If you could keep doing this if you want, but it's all programmed in Sage. So if you want data, I'll show you how to get data. I'm going to cover a theorem of Littlewood and Scharf-Thiebaud because that helps us get a combinatorial interpretation. So this problem has been considered over the last 100 years, this restriction problem from a GLN representation down to SN. It's been considered really kind of since the time of Schur. But the first traces of the progress that you could make on it are found in work of Littlewood in 1958, and then Scharf and Thiebaud reproved it using modern techniques because Littlewood's proofs are kind of opaque to me. I'm going to give a characterization of symmetric functions. So this is a tool that we use over and over and over. And I'm just going to kind of mark it. And I'm going to say, this is where I'm using this. I'm going to make it clear that like this tool works really well for proving identities in this. And then I'm going to give better definitions than pre-image of a single Schur function in the Frobenius map, because that it makes it clear how these symmetric functions really work as to give character values. Okay, so my recap is last time I said if I have a symmetric function, a symmetric function f, and it's going to represent a GLN character. It doesn't have to represent a GLN character, but if it's a symmetric function, can be evaluated by replacing the variables of the symmetric polynomial by the eigenvalues of a permutation matrix. And for this, I denote this by f of psi mu. And so I have my permutation matrix. It lies inside of Sn, and Sn is a subset of GLN. And so if I take a permutation of cycle type mu, and I ask what are its eigenvalues, they are roots of unity of a so they're roots of unity corresponding to the lengths of the cycles. And I showed last time, and I'm going to need this again this time, that pk of psi mu is equal to well, if mu is equal to 1 to the m1, 2 to the m2, n to the mn, then pk of psi mu is the sum over d divides k, dmd. And that's a formula I can apply Mobius inversion to, but I also have that p lambda of psi mu then is going to be the product for I equals 1 to length of lambda sum over d divides lambda I dmd. And so I'm going to need these two items for some of my proofs today. And then I define the Frobenius image to be, the sum over all cycle types, all possible cycle types. You evaluate the character at permutation of cycle type mu, and then you record the weight by p mu over z mu, and this is known as the Frobenius characteristic map. But when I apply it to a symmetric function considered as a character, as a GLN character, and I said my first definition of S lambda tilde, not the best one because it's kind of hard to get at it. It's the inverse image of a single Schur function for large n. Okay. Any questions? I calculated 2 examples of these. These were the simple examples. S empty was equal to the 1, and S1 tilde is equal to S1 minus 1. So S1 tilde is going to be the sum of all of the xi's minus 1. And that gives us a character value. So let's do this for n equals 3. I'm going to take my eigenvalues 1, 2, 3. The identity has eigenvalues 1, 1, 1. The permutation matrix for 1, 2, 3 has eigenvalues 1, minus 1, and 1. And the permutation matrix of cycle type 1, 2, 3 is 1, the third root of unity, and the third root of unity squared. And then S empty tilde evaluated at these eigenvalues. Well, it's just 1, so the eigenvalues are just 1. S1 tilde evaluated at the eigenvalues. Well, it's the sum of the eigenvalues minus 1. So this is 2. Sum of the eigenvalues minus 1 is 0. Sum of the eigenvalues minus 1 is minus 1. And if you know your character table, these are the first 2 rows of the character table for S3. The character table finishes by the sign character. And let's say I wanted to find that. So how would I do that? I'm going to compute S11 and evaluate it at all of the eigenvalues. And so S11, x1, x2, x3 looks like x1, x2 plus x1, x3 plus x2, x3. And if I evaluate that at x1, x2, x3 equal all 1, then I get 3. If I evaluate it at these eigenvalues, 2 of these monomials are going to be 2, and one of them are going to be, actually, these 2 are going to be, going to be minus 1, and this one's going to be positive 1. So I get in total minus 1, and if I evaluate it at the 3 roots of unity, I get 0. So what does that tell me? Well, I need to have this row here. How do I get that? I take this row and I subtract off this row. So I should take my S11 tilde. It should be equal to S11 minus S1 tilde. Okay, and then what I'm saying is that particular S11 tilde, if I evaluate that at S mu, it's equal to S11 minus S1 plus 1. And I'm going to get the third row of the character table. And now if I want to keep computing, I can do this all by hand, but I had I had programs for computing the Frobenius image. So I used Sage in order to say compute more data. And then I have these elements that I can multiply together and re-expand. And I can program that as a basis. And so we added it into Sage back in 2015, 2016. And so if you type into Sage symmetric functions QQ and you say inject shorthands all, then you get not only the standard bases, but you also get a few interesting character bases. One of which is this one that I'm describing here. The ST is shorthand for the irreducible symmetric group character basis. And HT is the one I'm going to cover today, is the induced trivial group symmetric group character basis. So it's the induced trivial character is its Frobenius image is H lambda. So I want a basis whose Frobenius image is a single H lambda. And if you compute the first few examples, the first thing you notice is that S lambda tilde is equal to S lambda plus lower terms. And if you look carefully, you'll also see that there's a sign, and that sign is very predictable, that this is sum over D greater than or equal to 1 minus 1 to the D, and terms of degree size of lambda minus D. But it's hard to say much else about them. And so this was a result of Sami Assef and David Spire. They actually proved that the S lambda tildes they have their top degree equal to S lambda, and lower degree terms alternate in sign. But they don't give any explicit formula for the coefficients.
Is there a question? Is there a certain rule on how to, for instance, in your last lower order example, you subtracted S1 to get the tilde. And is there a reasonable rule on how to do this?
No, you can give some formulas for the coefficients, but they are all very hard.
Mm-hmm.
Like they're hard to compute and they're hard to predict. So there's work to be done here.
Mm-hmm.
Like we would like to know the S tilde basis expanded in the Schur basis, and we would like to know the Schur basis expanded in the S tilde basis. And if you do that second one, that solves the restriction problem.
I see.
And that problem is hard.
I see. Is it equally hard if you do elementary other basis instead of Schur?
That's a very good question. And the answer is no, because that's one of the things I want to cover is that, I'm going to show that if you go from the H basis to the H tilde basis, and from this H tilde basis to the Schur basis, those are both predictable and easy to state. And it's a combinatorial interpretation that the transition from H to H tilde are in terms of these multi-set partitions. There's one term for each multi-set partition. And then the transition from H tilde to S tilde is to take the content of these multi-set partitions and turn them into tableau, column strict tableau in those multi-set partitions. And so the transition from H to S tilde is going to be where I'm going to show you, if I get that far, the multi-set tableau. So column strict tableau whose entries are multi-sets.
Mm-hmm. Okay, thank you.
Mike, I also have a question. So like, when you're doing the example on page 3, and you first compute S11, and then you know that, oh, I want to find the third row, and then I minus, so I know that is like what I want. But how do I know that the index is 1, the S tutor?
Well, so like I said, yeah, I have
Is
to.
it because of the,
But yeah, this one is going to be the leading term of this.
so you
uh,
already used that fact, right?
Yeah, and I know that phi 3 of S11 tilde is going to be, well, S111, right? It adds an extra long row on the first row, where extra long here is just.
Yeah, I know.
So I also had a question about this. So all we know that is that in the limit, if we add enough to the first row, that we get S tilde. How do you know that you can stop at 3? How do you know you don't need to take 5, 4 of and add more to the first row?
You don't so far.
You
It
don't.
works.
It works. Okay.
It works so far. Now I need to give you a real proof.
Right. And the other question that I had was going to your data on the next slide. It seems that even if all the coefficients aren't predictable, for example, the coefficient of S empty seems very predictable. Is that at least known? It doesn't seem to appear except for columns. And then it just switches back between plus and minus 1.
Yeah, S empty, you can prove that it is the only time it occurs is for S tilde column. And for S tilde column, you can prove that the expansion is exactly alternating. So there are special cases that you can prove.
Gotcha.
That's certain. I don't know how to prove in general.
Gotcha. Okay.
This is still something to do. I have on a last slide as well. If you want to play along at home, you can do this in Sage. That's, the operation of evaluating a symmetric function at these psi mu's is the function eval at permutation roots of mu, and the Frobenius image is this function character to Frobenius image, which allows you to compute the restriction coefficients, the restriction problem. So if I take the irreducible, I think even did something similar in my last talk. So the symmetric function with character S2 is Sim2 V4, and I'm asking, how does that decompose into symmetric group irreducibles? And the answer is with these terms. So there are 2 copies of the. So this says that this is a copy of S22 plus 2 copies of S31. Plus 2 copies of S4. And the fact that these actually do have the structure coefficients of the Kronecker product in the limit, so the reduced Kronecker coefficients, is not obvious yet, but hopefully it will be by the end of my talk, if I get that far. Okay. So the first result I want to prove is a theorem by Littlewood. This is from 1958. However, I would really credit this to Scharf and Thibon from 1994, because they went back to prove this in terms of modern notation and symmetric functions. The proof itself is not hard, but Littlewood did not explain it in any way that I understood. So let f and g be symmetric functions. F and g are symmetric functions. G needs to be a symmetric function of degree n in particular. Then the scalar product, so the operation which is dual to this phi n is plethism. And it's plethism by this series, this infinite series. Now, this object on the right, this is infinite, but if f is a symmetric function of a finite degree, it's going to be a finite number, and you can take the scalar product and it works out. So I'm not going to give the full proof. I just want to give an outline. You prove it for a basis. And so you take f equals p lambda and g equals p mu. And of course, mu needs to be a partition of n, and you set mu equal to 1 to the m1, 2 to the m2. Use the exponential notation for your partition mu. And then phi n of p lambda, coefficient of p mu, well, this is just p lambda evaluated at p, at psi mu. That was the definition that I gave for the Frobenius map. The Frobenius map gives a kind of all of the evaluations of this p lambda, and the scalar product with p mu takes out the one that happens to be p lambda psi mu. So now you need to compute the other side. So you compute p mu of 1 plus h1 plus h2. And what you need is that 1 plus h1 plus h2 is also equal to the exponential, so the product of r greater than or equal to 1, exponential of PR over r. And when you compute p mu plethism of, well, let me put this over here, p mu plethism of the exponential of PR over R, well, this is going to be the product for D equals 1 to n of PD plethism, the product of R greater than or equal to 1, exponential PR over R to the MD. And if you, I'm going to say proof left to the reader at this point, because the calculation is a bit technical, but the PD of PR is equal to PDR, and that's also true if you apply it to the exponential. So this is the product of D greater than or equal to 1, R greater than or equal to 1 of the exponential of PDR over R. And now if you group this into K greater than or equal to 1, and then you have to have that D divides K of the exponential of, I forgot my MD, PK over A over D. Raised to the MD, I can bring my MD inside. And now if you look carefully, what's coming out is exactly the expression that I gave for this thing right here. So take coefficient, and I get that this is equal to my product for I equals 1 to length of lambda. The sum of D divides lambda I. This is not equal. I want to say, take coefficient, you get this, which is precisely my P lambda psi mu. So this is what's going to get us our combinatorial interpretation in the end. So I kind of need that result. So I want to give a characterization of symmetric functions, and to do that, I need to make a connection between these character symmetric functions and character polynomials. And so character polynomials are in the literature, and they were first studied by Murnaghan in 1930s. So I want to make that the connection with the character polynomials explicit. So the character polynomial is for every symmetric function f, and the degree of f is less than or equal to n, there is a polynomial q of x1 through xn, and this is just a polynomial in the polynomial ring. And it says that for every mu equal to 1 to the m1, and it's exponential notation, 2 to the m2, n to the mn, that f evaluated at the roots of unity of mu is equal to q evaluated at those m1, m2, mn. And the proof is because of the evaluation of pi k, because I can say I define my q x1 through xn, it's equal to f, where I replace pk and I replace it by d divides k d xd. Because now if I evaluate my symmetric function on the left at the m's, that is the exact same thing as evaluating the pk's at the psi mu's, right? Because I recall that pk of psi mu is equal to the sum of d divides k, d and d. But the great thing about this connection is that if you have a character polynomial, you can also go back to the symmetric function. And the way you do that is you apply Mobius inversion, because I have done the substitution, pk goes to d divides k dxd. So that means that if I set F equal to Q and I evaluate it at P1, P2 minus P1 over 2, P3 minus P1 over 3, and in general, 1 over n, the sum of D divides n, mu of n over D, PD, I can recover my symmetric function F. So character polynomials and character symmetric functions, same thing. So these things have existed in the literature a long time. What we're doing here is that we make this connection between these two ways of evaluating characters. Oops. And now I want to give a characterization of symmetric functions. F is equal to G, so F and G are in symmetric functions, and the degree of F and the degree of G are less than or equal to D. So F is equal to G if and only if F mu is equal to G mu, say G mu, G of psi of mu for all mu less than D. If you evaluate F and G at enough points and those evaluations are equal, then the symmetric functions must be equal. So it's a way of proving symmetric function identities. If you want to prove that F is equal to G, you evaluate it at enough roots of unity and you say, these must be equal. And we've seen this before. I mean, this is a very typical technique. If you have a polynomial, if P of X is a polynomial in one variable, and the degree of P of X is less than or equal to D, then P of X is equal to 0 if and only if P of 0 is equal to P of 1 is equal to P of D is equal to 0, right? A polynomial of degree D with D plus 1 roots must be the 0 polynomial of at most D. So the statement that I'm making here is the multivariate version of that. Which, you prove by induction.
Do you really want if and only if there? You could have, oh, I see what you're saying. Gotcha. No, gotcha.
It's counterintuitive, but I'm gonna make a statement very similar. That if you evaluate something, it's the right thing. Like if you evaluate something, and it's true, then it's the right thing enough times. So this statement is also, it's something that we've seen on polynomials. It's a trick that's used to prove like A equals B, right? This is so the multivariate version that I'm not going to state the whole proof because it's you prove it by induction on number of variables and the degree, and you use that the single variate version. The multivariate version is that Q x1 x2 xd is equal to 0 if and only if Q of M1, M2, MD is equal to 0 for all M1 plus 2M2 plus DMD less than or equal to D, and all the MIs are greater than or equal to 0. And for a single variable, this is this statement up here. As long as I define the degree of xi is equal to I.
Mike?
Yeah.
Just a curiosity here. Would this be the proof, I mean, not the fact, but the proof for this one, would it be amenable to combinatorial Nernst-Lenz? Alon Nogas.
I actually don't, the Nernst-Lenz thoughts, I'm not sure. I proved it by induction, and then and you see that this is exactly the right number of points that you need.
Yeah.
And then so if you translate this back into what it says about symmetric functions in the last lemma, then you say, well, H is equal to F minus G, and Q x1 through xn corresponds to H. This that Q M1 Mn is equal to the evaluation of H at the roots of unity. So I'm going to call this property star. So this is I use this proof over and over again, but there's another identity that I'm going to use over and over again. It's that F is equal to G. So again, F and G are symmetric functions, and the degree of F is equal to the degree of G. It's less, or not equal, but they are symmetric functions. If both of these degrees are less than or equal to some D, then F is equal to G if and only if F evaluated at psi mu is equal to G evaluated at psi mu. But this time for all mu greater than D. If you evaluate it for enough points higher, it also characterizes F and G. And that's what we need in order to prove things in this. And so I'm going to call this also star, but a different star. And the proof here reduces to the previous case. So you reduce to previous case using the fact that if you evaluate F at psi mu, this time you add a part of size D minus 1, then this is equal to F of psi evaluated mu. So it's as if you add a really long cycle, it doesn't change your character value. And this is what, this is the answer to Brendan's proof from last time. He asked me, do the character values stabilize? And I said, yes, I think so, but I don't know for sure. The answer is yes. Character values stabilize if you add a one really long cycle, which is greater than the degree of your symmetric function. It doesn't change the character value. And so Now, if I say, let's say this identity holds for an infinite number of values greater than some fixed degree, then it also works for small values. And then this must be an identity. So then I can reduce to the previous case. So then now you apply. The other identity. Okay, so now I'm ready to prove my power sum expansions for these character polynomials and show how they all work. So I'm going to let b mu x1 xn be a form of z mu, but here's the polynomial, is if mu is equal to 1 to the a1, 2 to the a2, n to the an, and I let b mu equal 1 to the a1 and the following factorial of x1 a1, 2 to the a2, following factorial of x2 a2, n to the an, xn following factorial an. And the following factorial I'm talking about is x times x minus 1 down to x minus k plus 1. Then if you were to evaluate b mu at a1, a2, an, then so clearly b mu of a1, a2 to an is equal to z mu. Right? That's the way I defined it. But more generally, is b mu of m1, m2 up to mn, where I'm going to let gamma equal 1 to the m1, 2 to the m2, n to the n. Well, this is, first of all, the mi's need to be greater than or equal to ai's, and if not, the result is going to be 0. And if it is, then p gamma is equal to p mu times p tau, where tau is equal to 1 to the m1 minus a1, 2 to the m2 minus a2, and n to the mn minus an. And then the value that you get here, and I say you just need to do the calculation, is z gamma over z tau. So there's my character polynomial. Now I want to make a character symmetric function, and my character symmetric function, I'm going to call it p mu tilde, and that's going to be equal to b mu, where I evaluate this at p1, p2 minus p1 over 2, and so on. So I'm going to do this reverse engineer my symmetric function by evaluating the xi's at my Mobius inversion of my p's. D divides n. Mu of n over d pd. Then this is also going to be equal to p tilde mu at psi gamma. So here's a a symmetric function and I've given its power sum expansion, right? It's this weird polynomial in the power sums. It's these falling factorials evaluated at these expressions, but it is a power sum expansion for this element. So now I'm going to define two more symmetric functions. One is going to be an H basis, and one of them is going to be another Schur basis, but not the one we're looking at. So, so I'm going to say H mu tilde is equal to the sum over gamma partitions of the size of mu of H mu P gamma. And normally I would give the regular power sum here if I'm going to expand this in P mu, but now I'm going to put the P tilde right here. And I'm going to define a second basis gamma partitions of size of mu. And I'm going to put the scalar product with the Schur function this is a mu. Then proposition, and these are can evaluate each one of these, and they have exactly what they have some property that's going to help us get at our S tilde basis, which is not any of these three. The Frobenius image for any n of P mu tilde is P mu times Hn. In other words, you're inducing up to the trivial. So this is considered like a trivial thing that's coming in here. Phi n of H mu tilde is H mu Hn minus size of mu. And phi n of X mu tilde is S mu Hn minus size of mu. And these are all symmetric functions. I can control very precisely what their Frobenius image is. And they're going to help me get at this S tilde mu. And the way they get the, so let me just say proof. I'm not going to do the whole proof, but this is direct calculation for P mu tilde, and then apply phi n for n big to the other two. And deduce that it's right. My second identity. So here I can prove symmetric function identities by saying, oh, I'm going to apply my phi n to both sides of the equation. And if I apply it to phi n, and if it works for a big enough n, then that symmetric identity must be true. Again, I apply phi n to both sides of the equation. If the symmetric function identity is correct, then the thing is true. So the first one is definitely is not hard. You just kind of start from the left-hand side, you work your way to the right-hand side. So now I want to get at the S lambda tilde. And I do it in 2 steps. Whoops. X lambda tilde is the sum over lambda slash mu is a horizontal strip. All possible horizontal strips. S mu tilde. Proof, apply for n big. So I apply phi n and this for n big. And you can deduce then that S lambda tilde is the sum over lambda slash mu is a vertical strip -1 to the size of lambda minus size of mu x mu tilde. Then you can conclude that phi n of S lambda tilde. So if you take, you take this as your definition of my S lambda tilde, this thing has a power sum expansion. So now I've given the power sum expansion of this S lambda tilde. There are other ways of getting at the S lambda tildes, and I think the one that's programmed into Sage uses a different formula by Garcia and Goupil for the character polynomial, and that's actually more efficient for the power for getting at the power sum expansion. So I really like their theorem because if you get down under the hood, that particular character polynomial expansion that they give in their paper is just tighter when you get back to the symmetric functions. But then I can conclude here that this is going to be Sn minus size of lambda, comma lambda. And for n small, you have to do something special. You have to do this like the straightening algorithm with the short row on a Schur function, but that's not obvious. But this approach, taking the root of character polynomials to arrive at your S tilde basis, shows why they work, because they give you the right character values all the way around. And then you say, because the Frobenius image is the right thing, this is an identity that I know is true. So H mu tilde is the sum over lambda k n minus size of mu, comma mu. Whoops, I think it should be the other way around. Again, proof, you apply phi n and deduce the identity using star. So the expansion of the H mu tilde in terms of the S lambda, the S tilde lambda are these column strict tableaus with shape lambda, shape n minus lambda comma lambda. So it's got an extra long first row. And the content has an extra long set of entries here. So that those extra long set of entries in the column strict tableau, those need to be kind of filling up. They all have to end up in the first row of your column strict tableau. So so the interpretation, so this interpretation is column strict tableau with an extra long first row and a whole bunch of things that end up in that first row. And so we think of that kind of that long first row as being very flexible in its size. And so we draw our tableau with with kind of too long of a first row. And then I'm speeding through this a little bit too fast in order to finish. But now I've given the expansion of the H tilde in terms of the S tilde. I want to give the expansion of H lambda in terms of H lambda tilde. And so this is the sum over multi-set tableau pi. And there's one term for each multi-set partition. And m pi is equal to multiplicity. So it's a partition representing the multiplicities of the parts of pi. So let me give you an example of lambda is equal to 2, and I'm going to stop. So if lambda is equal to 2, the multi-set partitions look like this. There are 9 of them. And the weight for this one are the multiplicities of the parts here. And the first one are H22 tilde. The multiplicity in the parts in the second one, there are 2 parts of 2s and 1 part of 1, 1. This one has weight 2, 1. This one has weight 1, 1, 1, because the 3 parts, 1 occurs once, 2 occurs once, 1, 2 occurs once. These 3 each have different parts. This one has a part which occurs twice. This one has only 1 part, so it's H1. And so my example, the next identity that I'm going to prove next time which I'm going to need in order to get at our combinatorial interpretation for Kronecker coefficients, because I'm going to express that in terms of multi-set tableau. And multi-set tableau are the transition from sets to multi-sets, and then multi-sets to multi-set tableau. So my transition is H lambda tilde of mu is tableau, and then there's a weight for my tableau. And so my transition takes me from partitions to multi-set partitions, and then from multi-set partitions to multi-set tableau. And that's how I go from weight to multi-set tableau. All right. Sorry, I missed a few of the questions. I can try and answer those. I think the first one was do the tilde p mu's and the tilde h mu's mean that there's a symmetric function coming from restriction of the h and the p mu and the characters of GLN to Sn? These have less meaning on the characters of GLN because we are now restricted to symmetric group stuff, which is a subgroup of all of GLN. And yet we have, they have interpretation, but as symmetric group characters, but not as GLN characters. And then Anna.
Oh, my question was about the k n minus lambda, lambda n minus mu. So here, one of the partitions is smaller than the other, right? Or they don't have the same size, I suppose.
They don't have the same size.
Yeah,
right?
okay. Is mu smaller than lambda?
Lambda should be smaller than or equal to mu.
Yeah, okay.
Because those are the only ones that are going to be non-zero.
Okay.
All right, so let's thank Mike for a great talk. Any questions? Don't see any questions. So thank you, Mike. And next time we'll have Rosa, I believe, on Thursday, same time. All right. So I will see everyone on Thursday. Thank you, Mike. Bye.
Bye.
Thank you. Bye.